It is a real pleasure for me to be at this conference honoring such outstanding scientists like Cyrano de Dominicis and Claude Itzksen. And I'm grateful to the organizers for this opportunity to present some recent work. This is work done in collaboration with Sergei Rudkevich, who is also here at the conference. And I will also make contact to work on classical system where 4 other scientists were collaborating. Now, if a medium is confined by boundaries or walls or is by macroscopic objects immersed into the medium, then fluctuations induce effective forces between the objects. The most famous case is that of the Casimir effect, where one considers the effect of 2 metallic grounded plates on the electromagnetic field. The electromagnetic fields have to obey Dirichlet or Neumann boundary conditions on the plate, depending on the modes, and therefore the wave vector perpendicular to the plate takes on discrete values. And if you compute the energy, then you see there is a correction which turns out to be finite. There's an energy scale. The L dependence can be determined, follows from dimensional consideration. And there is an amplitude, a so-called Casimir amplitude, which is universal. It depends on the boundary condition, on the space dimension, on the dispersion relations of the photons, but is independent of microscopic details. This force has actually been measured for the first time quantitatively at the end of the last century. And it's studied very intensively for all sorts of systems. It depends also on the geometry. Now, 30 years later, Michael Fisher and De Gennes pointed out that a similar phenomenon should occur if we can confine a critical system. For example, you can take a fluid system near its critical point and confine it by walls. And then you can decompose the reduced free energy into a bulk contribution, surface contributions, which depend not only on the bulk universality class, but also on gross features of the surfaces. And there is a remainder, which I call residual free energy. And because of this L dependence, you have, of course, a reduced Casimir force per area. And one can gain information about the form of this force by invoking a finite size scaling argument. So if you assume that the only length that matters besides the separation of the walls is the bulk correlation length, then you write down such a scaling form, and the scaling function should be universal, again, independent of microscopic details. And as you approach the critical point, this scaling function goes to a constant, and we recover a Casimir amplitude. And the force is then the derivative with respect to L of this, I think. And this has been measured some time ago indirectly by looking at wetting layers of helium on substrates and then going to the lambda transition, and directly by Clemens Bechinger's group in Stuttgart, who is now at Konstanz, for binary fluids. Now, in this talk, I would like to consider bosons confined to such a strip. This is interesting because bosons are, of course, quantum. We have a quantum mechanical system, so we have both quantum fluctuations and thermal fluctuation. And for bulk systems with d larger than 2, there is a transition to an ordered phase, so we have also thermal transitions. And it will be interesting to consider various boundary conditions like periodic, antiperiodic, Dirichlet on both plates, Neumann on both plates, Dirichlet on one, Neumann on the other, or Robin boundary conditions either on one or on both plates. Robin boundary condition is a boundary condition of this form, where the C1 can have one value on this plate and another one on the other plate. And we will consider 3 cases. We will allow either a potential energy of the standard form, short-range interactions with n components, because we eventually will take a limit n going to infinity. We will look at the ideal case first, and we will look at a model which is called imperfect model. This imperfect Bose gas it has a potential energy where each pair of the bosons contributes the same amount to the potential energy. This, of course, makes only sense if you have a periodic boundary condition, because otherwise it would not be physically reasonable to take them all. So it's like a defective long-range interaction. And we have the usual commutation relations. And so let me then look first at the ideal case. One can compute the grand partition function and decompose then the grand potential per area in terms of a bulk term, a surface correction, and again what I call a residual potential. The residual potential has this L dependence. Now in the ideal case we have two important length scales. One is the thermal de Broglie wavelength, the other is the correlation length, which for the ideal case has this form. And so we can write down the scaling ansatz for the residual potential of this form. It has two scaling variables, and here there are of course quantum effects via the de Broglie wavelengths. And this is a simple exercise for students to compute the bulk potential. A little bit harder is to compute the surface contribution for various boundary conditions like Dirichlet and Neumann-Neumann. But again, this can be done in this form. Considerably more complicated is to compute the scaling function, including quantum effects, for the residual potential. And this was done by Martin and Zagrebnov for the three-dimensional case and the periodic Dirichlet and Neumann boundary conditions in the form of a double series expansion. Since they had the full information, they could also look at the behavior near criticality and look at the classical part. So you expect near the transition for there's a TC larger than 0, you can take this limit and then you should get a classical scaling function. Unfortunately, they did not make the connection with classical models, but it was pointed out by Gambassi and Dietrich. If you analyze their series results, then you actually find complete consistency with earlier results for the massive free field case for a two-component O2 theory. And well, one can generalize this for all D. As an aside, let me remind you, you will all know that the critical exponent of the Bose gas differ from those of a Gaussian model, but that's nothing to worry about because in the Bose gas one keeps usually the density fixed, and Michael Fisher told us decades ago that this is a constraint which leads to a Fisher renormalization of exponents, so the exponents of the Bose gas in the free case are nothing but Fisher renormalized Gaussian exponents. Here are results. I mean, if one looks at the case in 3 dimensions, one can do a little bit more. One can actually resum the series for the classical scaling function and get them in closed form. You see for periodic, antiperiodic, Dirichlet, and Dirichlet-Neumann boundary conditions. And as you see, in these cases, periodic Dirichlet, Neumann, so I mean like boundary conditions, the function is negative, which means one has an attractive interaction. And we know from rigorous work by Bachar and Kenneth and Klitsch that this has to be the case. On the other hand, for unlike boundary condition like Dirichlet-Neumann and also in the antiperiodic case, one has a repulsive interaction. Now what about the Robin case, which is more complicated, and what about quantum corrections? Now, the Robin scale, in the case of the Robin boundary conditions on both plates, we have two more arguments because we have two surface variables which enter in scaled form here. And one can derive such a result. So this is the classical part, which comes from the zero Matsubara frequency portion. And then there are corrections from quantum corrections, which are exponentially small and become smaller as you go along this series. And you see here is this function in explicit form. It also, we cover from that the Dirichlet-Neumann and Neumann case by choosing setting C1 to 0 or infinity, and we gain all the other cases. And the quantum corrections, I show here just the case where you are at criticality. So you have an amplitude, and here are the quantum corrections, and you see the decay lengths. If you compare that with the periodic or anti-periodic boundary conditions, the decay length then differs by a factor of 2, which can also be easily understood. Now, let me move on and consider the imperfect Bose gas. So this is this Bose gas where all pairs contribute the same amount to the potential energy, and this is well defined for periodic boundary condition. This was solved by Jakubczyk and Napiorkowski exactly. One gets a contour integral over the partition function of the free case at imaginary complex chemical potentials, and one can evaluate this by saddle point integration. And what they found was the critical exponent were exactly those of the spherical model. And then there were apparently to their surprise, they found that the amplitude was twice that of the spherical model. And they didn't look at the scaling function. Now, so the question they posed was, what is the universality class? Now, it's not something that you can easily understand. The universality class is that of an O2N model, because we now the boson field is a complex order parameter and has 2 components, so n component complex means 2 n component real, and one can in fact see that this corresponds to the O2 infinity model of the phi to the 4 model. The way to see this is to really look at the n going to infinity limit of this Bose gas model with typical short-range interactions. One can use a coherent state functional integral representation and then look at the large n limit and a stationary point functional integral. And what you get is a self-consistent equation with a potential of this form, and this potential is independent of z if you have periodic boundary conditions. So that makes life a little bit easier, but what is very hard if you have free boundary condition like Dirichlet boundary condition, because then this is z-dependent and you get up typically self-consistent Schrödinger equations. Now, let me show you first what one gets in the case of periodic boundary conditions. So in the case of periodic boundary conditions, the scaling function for the classical spherical model, mean spherical model, was computed by Danshev. And one can show what we did is we recover this up to a factor of 2, as it should be, from the proper limit of the Bose gas model. And here you see the behavior. I mean, it goes down, and this is the transition. At TC, it goes down and then saturates here. Now, the connection with the n-component Bose model is nice because we can now ask ourselves, can we generalize the imperfect Bose model for the case of non-translational invariant boundary conditions like Dirichlet boundary condition? And one can do that, in fact, because we just have to look at the large n limit. And what you get then is you have to use this potential energy, you have just to keep track of the z-dependence of the number operator. Right? And finally, we can also look at the case of Dirichlet boundary conditions and study the large n limit, and we know the connection with the O2 infinity phi to the 4 model, which was studied with these four other gentlemen in a series of papers, and I can only mention what we were able to achieve. We solved the self-consistent Schrödinger equation numerically, which is tricky, many issues which come up, corrections to scaling and so on. Numerically, we solved this on the one hand. On the other hand, we used a bunch of analytical tools to get exact results. So we used boundary operator expansion in conjunction with a short distance expansion. And then we used a generalization of inverse scattering theory to cope with a singular potential. And we were able to get the scattering data corresponding to the self-consistent potential for the semi-infinite case exactly. And then to cope with the constraint system, we used matched semi-classical expansion and also needed a new trace formula. Let me just show you the results we were able to obtain. Note first that the scaling function now is qualitatively different from the case of periodic boundary conditions because it goes up again. It has here the deep minimum and then goes up again. And this is qualitatively the same as what one saw in measurements of wetting layer for helium. So qualitatively, this is the same. And we were able, using these exact results, to get the asymptotic form in the low temperature regime. This is a trivial case corresponding to the Gaussian free field theory with Neumann boundary condition. Then the first correction here, and there is an anomalous correction which comes from the Goldstone modes. So we have a good understanding, and this is the end of my talk. I think time is up, so let me just summarize again what we did. On the one hand, the ideal case, the imperfect Bose gas, and then the connection with the large n limit of Bose, and looked also at the quantum corrections. Thank you for your attention.
Are there questions? Jean?
What is real physical systems? The temperature range where you have competition between quantum and
Yes, yes. Well, we did not look, I mean, you can also ask the question, look at very low temperature, very low temperature, and that's of course much more difficult because then, I mean, there's even not good knowledge. I mean, the only knowledge at the really low temperature case for these kind of models is from exact renormalization group, Wetterich group, and so no, we did not, we did not, I wouldn't know how to do that analytically to really handle this.
Now, what concerns the Casimir fault has been measured at the level of 1 micron, between 1/10 of a micron and a micron. So that's, yeah.
Well, I'm not aware that so far there are no experiments which have measured that. I mean, usually what has been done so far is people usually look at the case where you have bosons in a trap, right, and these things.
Yes?
What is the parameter xc?
Xc, this is just L divided by the correlation length.
The correlation length is a quantum length.
No, it's the correlation length at the transition. The other one was called x lambda. So, right in. Actually, I mean, if you are in the three-dimensional case, because the correlation length exponent is exactly 1 for the spherical model, so this is just L times temperature, properly normalized, right, the scaling variable. But in general, it's L times psi to the 1 over nu, right?
Other questions?
Sure. The Robin boundary condition is essentially an absorption on the plates, right? Because it's a very quick, but a very quick derivative.
I'm not sure I understand. What do you mean with
Absorption? It's an absorption interaction on the, because
are you talking about the classical case or?
well, in the classical case for
I mean, this is in the boundary conditions. You see, I mean, if you take a classical phi to the 4 model, then there's a quadratic term c times phi to the phi squared, and the c corresponds to short-range potential. And if you have in mind binary liquids, then of course you would also have to add a surface field, which I did not do here, right? I mean, surface field because you generally have a one-body potential also. Okay.
Okay, thank you.